Maria, you want to give it a chance, try to share your slides, and let's see whether or not we've got a.
Yeah, let's see if it's. How does that look?
Looks fantastic from my side. Thank you very much. I'm so glad to have you here today and for kicking off our morning session. I will try my very best to give you a 2-minute warning. Our sessions this morning, our talks this morning are 15 minutes plus 5 for Q&A. And if I can't interrupt you, I'll come screaming in at the 15-minute mark.
Okay, sounds great.
With that, I'll hand it over to you, Maria. Thanks very much.
Okay, awesome. So first of all, I want to thank all the organizers for asking me to come and talk to you about synergies between LISA and the Reuben Observatory's Legacy Survey of Space and Time, which most of you have probably heard of as Lsst. So I'll dive right in and see how far I can get through this. There's a lot of science overlap, so I'll cover what ground we can. So you heard all of this tomorrow, so I'm going to be real brief with an intro on LISA, but essentially, reminder, we are looking at a new window on gravitational waves from what we've been doing for the last several years with LIGO and with existing pulsar timing arrays. We're really looking at these megahertz frequencies of gravitational waves when they come online. And there's a lot of things LISA is going to do and see and look at, but we mainly have been focusing on these 3 kind of broad classes of different sources that will be observed in gravitational waves by LISA. So in spiral of massive black holes on the sort of millions of solar mass regime, extreme mass ratio in spirals, and then the galactic compact object binary. So things like double white dwarfs, but also things like white dwarfs and neutron stars, and even as I'll get to strip stars and white dwarfs and neutron stars. So a lot of different compact object binaries that we'll see during in spiral and mergers as well over long time periods. So, and as we get to the synergies with our electromagnetic observations, in particular from LSST, things to just keep in mind, again, this was mostly talked about in some of the talks yesterday and sort of later, things like gravitational waves. So what is LISA going to give us for those sources? Because the idea with multi-messenger is you are trying to get new and different information from 2 different messengers, so in this case, gravitational waves and EM light. So what LISA will mostly give us, this is not an extensive list, but some of the things you should just have in the back of your mind as you're thinking of these 3 types of sources. They will give us masses for the systems, most sensitive to a combined chirp mass, so with some constraints on sort of the individual mass of the 2 systems, periods and period derivatives, some constraints on the distance, the spin, rough sky localizations that vary from a few arc minutes in the best cases to tens of degrees and eccentricities. Those are the types of things that gravity will be probing. So what about the Reuben Observatory? I want to make sure everyone is on the same page before I get into the details of those 3 source kinds of what it is, what data it's going to give us, and how Canada is involved. So the really high level Reuben is, it's an 8.4 meter telescope located down in Chile. This is an image of it a few years ago now while it was under construction. And it has a mega huge camera on it, 3.2 gigapixels that will provide 0.2 arc seconds per pixel over a huge field of view, 9.6 square degrees. So what you should be thinking is this is a really large telescope that is going to get very nice images over very large patches of the sky all in one go. And in particular, unlike many other telescopes of that aperture, it is dedicated to survey operations. So what type of data are we talking about specifically? It's divided into a few chunks, but the main one is the main survey, which is called Wide, Fast, and Deep. And the baseline is that it will be a 10-year survey where they will cover the entire southern sky, about 18,000 square degrees, every 3 nights. And that has an asterisk, I'll come back to that, in 6 different filters. So UGRIZY. So things basically what you can do with a silicon detector. So from the atmospheric limit all the way to about 1 micron. The images are going to be superb. A single image depth in only about 30 seconds will get you to 25th magnitude in G. And the 10-year image depth by stacking together different things will be about 27th magnitude in G. These are unprecedented depths for things from the ground. The main thing I wanted to say in terms of that asterisk is that every 3 nights, it's not going to be doing every filter every 3 nights. It will observe the patch of the sky in some filter every 3 nights. Your typical cadence in single filter observations is going to be more like 1 to 2 weeks, depending on the exact survey strategy, which is still being decided. So in addition to this main survey, some fraction of the time, approximately 10%, is also devoted to special projects, things like mini surveys or a few targeted deep drilling fields where they will be observed much more frequently and get to even deeper depths at higher cadences. So the main data products that will be coming out of LSST, there's a couple different classes, each of which will allow different synergistic science with LISA. So in particular, LSST will be processing data in real time and sending out alerts on objects that change in their brightness. And the delay that they are quoting for that now is that within 60 seconds of an image being taken, you will be able to get an alert if some object in the sky has changed its brightness. In addition to that, there will be nightly images and updated static catalogs that are updated on a 24-hour time scale. And then there will be yearly data releases with different sort of deep stacks with images summed over different amounts of time. So you can imagine this is an insane amount of data. And so a huge part of the community effort right now is how are we going to deal with that data volume and get everything in place now so that we can actually utilize this to do science going forward. So what is the timeline for this? This is a somewhat old timeline from a couple of years ago, but we are actually, you'll see sort of all the way over here on this side. But basically science observations are expected sometime in the 2023-2024 time range. So within the next year or two, this 10-year survey should start. So the biggest things that I want to emphasize in terms of synergies with LISA on this time scale is that there will be a significant baseline of LSST data prior to when LISA would actually launch and start giving gravitational waves. So we can utilize the fact that there is going to be this almost full 10-year baseline survey over much of the southern sky available at the time of launch. In addition to that, though, it's not been announced exactly what this telescope will do after the 10-year survey is completed, but unlike some limited lifetime satellites that are discussed, the telescope's not going anywhere. It will still be there on the ground. So assuming that there is operations funds, something will happen after the 10-year baseline. So in terms of the science synergies that I'll talk about shortly, I am assuming both that we will have this huge, amazing data set prior to LISA starting, but also that commensurate or same time observations will be possible because the telescope will still be there. So what is Canada's involvement in LSST? This is a project that is led out of the US, but the mechanism for other countries to be involved is that there is an in-kind program where other international partners can provide some sort of resource that will aid the LSST project as a whole in exchange for data access and rights. And so Canada has such an agreement with the Lsst collaboration. The details of it are evolving over time as we apply for more funding to basically boost our contributions. But the status of it now is that Canada has is contributing basically directable efforts of 7 Canadian Reuben Fellows. So people who would be developing software for use in doing science with this data. I'll come to this again at the end of the talk, as well as a Canadian Public Data Archive. But with this, a significant fraction of the Canadian community is going to have access to LSST data going forward. Okay, so with that background for both LISA and then the types of data that we're hoping to get from LSST, what sort of science can you actually get by combining LISA with LSST? I'm going to step through these 3 main classes of objects that I mentioned at the beginning and highlight for each of them. First, I'll start by just highlighting a few science themes for each of them that are facilitated if you have both gravitational waves and EM counterparts. Clearly, there's a lot of science LISA is going to do on its own, but I'll highlight just a few science themes for what you can do if you actually are able to get EM data as well. And then try to highlight specifically what types of data LSST will be able to use to advance those science themes. I'm going to be a bit broad. There's a lot more information elsewhere. There are, of course, many other types of multi-messenger synergy across the electromagnetic spectrum. I'm going to be focused on the optical, mainly because of the connection to LSST, but I'll put this up and my slides are available online. There's a lot of really great resources on this. In particular, there's a white paper that goes through like many of these multi-messenger science cases with megahertz gravitational waves. there's the Lsst science proposal, and then also just a few weeks ago, the Transient and Variable Star Collaboration within Lsst put out a new roadmap for basically what is the path forward to getting the most out of this data set. And that really works through what types of things are expected across a wide range of science platforms with Lsst. So I have linked to all of these together as well. Okay, and with this, as we go through each of these, sort of in the same broad brush way I had at the beginning of what broad types of information can you get from gravitational waves? What broad types of information are you getting from light? And the main thing we all know is that light is probing matter. And so much of what we're going to get from Lsst or from any other electromagnetic counterparts are things like galactic and stellar light and everything that comes with those. You're going to be probing things like accretion onto compact objects as well as outflows. Anytime you have a transient where material is thrown outwards, EM can probe that. We can also probe things like the local environment and physical context where these mergers are occurring, as well as things like redshift. And all of those are things that are relevant and are material things that are added to what you get from the gravitational waves themselves. Okay, so diving in, what can we do with the in-spiral and merger of million solar mass black holes? There are three themes I'll highlight briefly for this. Again, this is not all-encompassing of multi-messenger science here, but when you couple together gravitational waves from Lsst with EM emission, you can do tests of Landis-EM, oh wow, that's not the right acronym, Landis-EM cosmology. You can learn about the evolution of supermassive black holes with their galaxies, as well as the growth of the earliest black hole seeds. So with this first one, the main thing to highlight here is that Lsst can provide luminosity distances of massive black hole binaries out to Z of about 3. However, if you want to get the redshifts, and so to put them on a Hubble diagram, you need EM observations. There are degeneracies within the gravitational wave data itself that don't allow you to get the redshift out itself. So if you want distance versus redshift, you need to identify somehow the host or the specific galaxy that these mergers were occurring in. And that can be done with electromagnetic light. Similarly, with the coevolution of supermassive black holes and their galaxies, we know that nuclear supermassive black holes correlate with various properties of their galaxies. And if you can relate a merging black hole, and again, these million solar mass cases, so slightly lower mass to their specific galaxy, you can start to probe those correlations and relationships over a wide range of luminosity and mass and how those two things grow and evolve together over cosmic time. But that requires knowing what specific galaxy the different Lsst mergers actually occur in. And then this is a case, I'm also highlighting things where you might have complementary science where gravitational waves and EM sort of look at opposite sides of the same scientific coin. So we want to learn how the earliest black hole seeds grow. Lsst is going to probe the assembly of million solar mass black holes via mergers out to Z of 20, since it's sort of the beginning of the universe. But EM observations at the same time can probe the growth of those same black holes via accretion. So again, mergers and accretion are the main ways we think that these earliest black holes grow and form. And I think by coupling together studies of mergers from gravitational waves and study of accretion in these very early quasars, we can start to put together pieces as a whole, but you really need both parts. It's, for instance, from electromagnetic observations that we know that billion solar mass black holes had to form by Z of approximately 10 already. And so it's useful to get the electromagnetic light to study accretion on the opposite side of it. So what do you actually get from Lsst? You'll notice that a big theme in much of that previous case was, in order to do most of that type of multi-messenger science, we actually need to identify or localize the galaxies where Lsst mergers are actually occurring. And this is something that hopefully Lsst can actually help us with. And one of the big data sets that we're going to get is even prior to Lsst operations, it will be able to give us long baseline records of AGN variability. This can let you search for periodic signals. This is just one example of something that's been done with a previous time domain survey. And this both can be helpful in terms of identifying things that are good candidates for Lsst mergers already. There are predictions of precursor emission from Lsst mergers where sort of various periodicity or flaring might be evident up to decades before when the merger actually occurs. So this can be used to find actually good candidates for mergers that will happen, but also provide a frame of reference for once Lsst is running. If you want something where, okay, we know there's a merger from Lsst in this rough patch of the sky, is there any AGN or variability quasar that has changed its behavior and is now doing something different than it was for the baseline of 10 years prior? So it both gives that previous baseline and it allows you to search for signals that might be indicative of a merger happening in the first place. This is just one piece of how we might actually couple together and figure out where these mergers are occurring directly. In addition, you can get deep galaxy catalogs from LSST. This is important because for the context when you don't actually identify this is the host galaxy that one of these massive black hole mergers occurs in, there are methods to actually go through and still do some of the cosmology science cases from a statistical perspective. But in order to do that, you need pretty complete galaxy catalogs. So you know what is the range of possible hosts for each merger within the localization regions. And you need to be complete down to fairly deep limits out to the types of distances where Lisa is actually observing these. So having the very deep images from LSST will be very helpful for this. And finally,
Maria, you've got 2 minutes.
Perfect. Yeah. I'm going to speed through the rest of this then. It's also useful for the high redshift AGN searches where you basically do not expect optical light. So it's great when you couple it with JWST. So for the other two cases, which I'll just spend a minute on each, miscalibrating time, for the extreme mass ratio in spirals, the main science contexts you can get from this are the existence and formation of intermediate mass black holes. Well, Lisa can probe this directly. If you get an EM counterpart, you can start to localize the environment directly for a lot of the stuff that Greg and others were talking about yesterday. Are they globular clusters? Are they off-center from their host? Where are they? Tidal disruptions of white dwarfs around IMBHs are predicted to produce transients. And then similarly for dynamics in galactic nuclei, while Lisa and Emery's are going to probe compact objects around supermassive black holes, EM objects can produce tidal disruption events from stars around them as well. So that's complementary science, opposite sides of the same coin. So much of this is about IDing tidal disruption events. And this is something that LSST should be great at. There are predictions of thousands of events per year, but in this prompt identification and exact survey strategy are going to be vital for allowing us to get follow-up observations we need. LSST will find them, but it won't get all the detailed follow-up we need on our own. So that's something where there's a lot of work. And then finally, with the galactic compact object binaries, there's a lot that we're going to probe from EM by learning about the fate of these stellar binaries, because you can get things like EM observations are critical for determining evolutionary state, as well as individual masses to couple with the information from Lisa, as well as the physics of mass accretion in these systems, as you have things like gravitational waves are affecting angular momentum transport, but so is accretion onto the objects themselves. And it's EM observations that will allow you to probe things like accretion luminosity as well as tidal heating. And the main thing is that LSST is going to be amazing at basically identifying many of the compact object binaries that Lisa is expected to see. These objects are going to be very faint, so you need good image quality, but they are expected to be very tight binaries and so show ellipsoidal modulations, which you can pull out from long time series data. So even though you're expecting things like periods of only minutes, it's been demonstrated with things like ZTF, which I'm showing here, that you can pull out this information from sparsely sampled data with things of only a cadence of a day or two. You can pull out these very tight period binaries from that data. So it is going to find a lot of Lisa verification binaries as well as the populations that we need to do this multi-messenger science. So with that, I will just highlight there's a lot of different things that LSST is going to give us. It's going to be the primary mechanism for finding these object-to-object binaries in the galaxy that we can do. And finally, you should come work with us on this. I mentioned that Canada has a number of these Reuben fellows that we are hiring. These are 3-year positions, of which 50% are supposed to be software development and 50% is your own science. The software development, though, is explicitly to enable science to be carried out with LSST data. And we are hiring this year in particular for someone to sit in the transients and variable stars collaboration of LSST and one to sit in the AGN working group with LSST and figure out what do we need to actually pull science out of this data and start developing those tools. And those are the 2 working groups that most of this multi-messenger science with Lisa is going to come from, transients and variable stars and AGN. And so please reach out to either myself or John if you have questions about those. Thank you very much.
Awesome. Thank you, Maria. So that's our full time, but if anybody has a quick question for Maria, I'm happy to entertain it. You can raise your hand or just unmute. I see one from Eric in the chat, Maria. I'll read it out to you. If I'm understanding correctly, LSST will help ID potential mergers. Confirmation would be assisted via modeling once a potential merger is ID'd, question mark.
And so are we talking the massive black holes? Or are we talking stellar mergers? In which of those cases are you?
Massive black holes, sorry.
So basically modeling whether like the types of light curves that we actually see, like the periodicity is actually what's going on. Or in the case of like commensurate with Lisa, there will be occasions where we know, okay, there's going to be a merger happening in this patch of the sky, and we can basically point LSST in that direction and see if there's any prompt emission. And so you're right, we can do things there. Yes, you need to model any transient that you discover that's associated with it and figure out, does this make sense for that that's what's actually going. So yes, you could say that they are candidate counterparts to those mergers, but you'll have a lot of things with like temporal information, like how coincident is it with the Lisa in spiral. You'll have a lot of really great timing information from it. So it's better than some other cases.
Okay, awesome, thanks.
Yeah, great. All right, everyone, please keep that conversation going in the chat. Maria